Hello everyone, welcome to Stat 310 Lecture 20. And so today we're going to finish our discussion on Chapter 12, which covers the analysis of variance, which is a very important tool in statistics when you're kind of dealing with, discrete factors that are used to predict a particular response. So we kind of saw that if you have a factor like, whether someone belongs to a particular state, whether that's going to influence, who they vote for example. You kind of want to, you don't want to treat all of the states the same. So you kind of want a model that incorporates that. And so we saw how that kind of works with one-way analysis of variance in 12.2. And so today we're going to look at when you have kind of two factors that influence that response. And so that's two-way ANOVA, which is a very kind of widely used tools. So just to recall what we learned about one-way ANOVA in lecture 19, because that's going to kind of be the basis for two-way ANOVA. Essentially, the ideas are very similar and the key components of what we learned kind of remain the same, but things get a little bit more complicated when we have two factors, as we'll see. So recall that. So I'm going to kind of break down what we learned in lecture 19 for one-way ANOVA into 6 key components. So the first one is the data. So the data here is Yij. So you have two subscripts here. One is kind of I between 1 and I, where I is the number of samples, or is the number of different groups. So you can think of that as like the number of different states. So I is like the number of different groups, or the number of different factors, and J is the number of samples for each group or samples for each factor. So we kind of assume that they're all the same, and that's kind of a nice simplifying assumption. The second key component is the model the general kind of model that we use. And so for one-way ANOVA, so everything I'm saying is for one-way, and what we're going to do in this lecture is derive everything for the two-way case, or present everything for the two-way case. So we have Yij, which has this mu, which is kind of the overall sort of mean of all of your data. Alpha I is kind of the effect of each group. And then we have noise. And so we have this assumption that the alpha i's must sum to 0 because you have the overall mean mu. The group effect kind of on average, when you add it all up, has to be 0. And the epsilon ij's we kind of always assume to be normal with the same variance. And then the estimators of our parameters. So the key kind of estimators here are for the mu hat and for the alpha I hat. I'll briefly talk as well about how you estimate sigma hat squared. I didn't talk about that in the previous lecture, but I will talk about that here briefly. So here we have mu hat is kind of the overall mean. So I've used this notation y bar dot dot, which is just the overall mean across all of the I groups. And then alpha hat I is kind of the group effect. So that's like the mean of each group, but then you want to subtract off the overall mean to just get to isolate the group effect. And then in terms of, that's kind of the estimation side of things. But if we want to put it into a hypothesis testing kind of framework, the key component that we need for hypothesis testing is the null hypothesis. So the alternative is just the complement of the null hypothesis. So the null hypothesis just asserts that there's sort of no group effect. So alpha 1 through to alpha I are all 0. And so the key thing that we're going to use to sort of build towards the statistic that we test the null hypothesis with is the so-called analysis of variance decomposition. And this is probably the most important concept in this, which is that in some sense it's called analysis of variance because you're looking at the variance across the whole sample, and you're getting a sense of how that variance, how that variability or variance is distributed across the group. So we have this kind of nice form that the total sum of squares is equal to the sum of squares between the groups and the sum of squares within the groups. In some sense, the sum of squares total is just Yij minus mu hat squared. So it's kind of like saying if you just looked at the overall mean and subtracted that from Yij. And then the between group sum of squares is this J is kind of at the front to kind of make the sums all add up. And then sum of squares between group is just the sum of the alpha hat I squareds. And then the sum of squares within the groups is, if you kind of look at the model with the mu hat and the alpha hat I and subtract that off, then like the sum of squares within the groups is just like yij minus mu hat minus alpha hat I squared. And the other key component is the degrees of freedom, because like you can kind of view all of these as chi-squared random variables with some degrees of freedom. And how you calculate the degrees of freedom is really important. So for the total sum of squares, because there's only one parameter involved in ij samples, it's ij minus 1. For the between group sum of squares, because you essentially have I parameters like the alpha i's, that's why you get I. But then you also have this constraint that the sum of the alpha i's is 0. So that kind of gives you the degrees of freedom I minus 1. And then for the within groups, you have I times j minus 1 degrees of freedom, because in some sense, like you can interpret it as there's I groups, and for each one, you're kind of finding like, you're kind of losing 1 degree of freedom because you're estimating the overall sample mean. So that's why you get I times j minus 1 degrees of freedom there. And that leads to kind of the analysis of variance in the F-test, which is really critical. So in some sense, like you're in some sense breaking down the how the variance decomposes, and then your that's going to lead to an F-test. And so because it's kind of the ratio of two chi-squares. So in particular, the degrees of freedom, I'm essentially just summarizing what I've said earlier. The degrees of freedom you put down for the between, the within, and the total, and the between plus the within should add up to the total here for the first two columns. Then you look at the sum of squares, which I put the formulas up for. And then the last two columns, first you look at the mean squares, which is just the sum of squares divided by the degrees of freedom. So it's the sum of squares divided by the degrees of freedom. And then the F statistic, which looks at the ratio of the two mean squares between and within. So sum of squares between and sum of squares within. And in some sense, like under the null hypothesis HA here, the HA, I'll talk about why I use HA shortly, because we're going to have different nulls as we go through. That has this distribution of like F statistic with I minus 1 and then I times j minus 1, because it's the ratio of chi-squares. And this was all covered in the previous lecture. I thought it was just worth reminding us, because this is going to be kind of the framework we're going to work in for the two-way and over. And then I just also want to quickly mention, this is not the most important thing, but I just kind of wanted to mention it. How do we estimate sigma hat squared? There's a very straightforward estimator, which is just the sum of squares within, and then we divide by the degrees of freedom. So this is like kind of, it's analogous for the two sample case that we learned about in chapter 11. This is basically just like the pooled standard deviation. So this is extension of pooled estimate for variance in chapter 11. Okay, but you don't actually need to compute this to do the F-test. But if you are interested in estimating sigma squared, this is how you do it. And the same logic will apply for the two-way case that we'll go through shortly. So now let's move on to kind of the main topic that we're going to cover today, which is this two-way ANOVA. And so this is kind of like, it's just an extension of the one-way cases. What if you have two factors that influence the response? And we're essentially going to derive those 6 key components that I spoke about earlier in the two-way ANOVA case. And so, like, if you want to just think about examples, so let's just again go back to voting. Let's just say that, like you want the state effect. The the state effect, and then you may also want like say a say the education level effect, for example. And I could add a lot of other effects too, like I could add gender, and any other effect that I'm looking at. But here we've got two factors that so we have two discrete factors. Two discrete factors influencing the response. Okay, and so if you look at the data here and how we denote it, we're going to say that it's Yijk, where I is less than 1, less than I, J is less than 1, less than J, and then I'm just using the same notation as in the book. K is less than 1, less than or equal to big K. So I is the number of I guess we'll say the the first I guess we'll say the number of levels or groups for first factor. So e.g. you could have 52 states. J is the number of levels or groups for second factor. Okay, and so for example, we could say that that's just the number of different education levels we consider. So for example, and this depends on how the data is recorded. It might be recorded as, you're looking at people who graduated high school, people who graduated, or people who didn't graduate high school, people who graduated with a college degree, and so on. So that's kind of the type of levels that we're talking about. And then K is the number of samples within each I'll say a group. So a group here kind of means that you look at a particular a state and an education level. So you might be talking about, for example, like the if you look purely at Wisconsin, if you look at purely at Wisconsin and people who have a college degree from Wisconsin, that's what I mean by and the number of people that you look at from that particular group. So once again, we're kind of assuming that K is the same across all of these different groups, and now groups have two factors that determine kind of the identity of that group. So it might be people who graduated college in Wisconsin, it might be people who graduated high school in California, or something like that. And so you have two factors here that influence the response, and K is the number of samples within each of those kind of subgroups. So I'm just going to kind of put down an example from the book just to kind of get you kind of acquainted with this. And so and then this is looking at how much energy is used by an electric range in a restaurant. And here we've got two factors. So we have the menu day, and then we have the range used. So the restaurant has a bunch of different ranges, in fact, 3 that we look at. And so this is in page 489 of the textbook. And I'll just sort of write that down. So we have the menu day, and then the range. So we have 3 different ranges. and then 3 different menu days, and then the different values according to the y's there. So this is y11 1. And this is just essentially just copying what's in the book just to give you just a sense of what this kind of data might look like. There's lots of other examples too. Okay, and so here in this particular case, we have I equals 3. There's 3 menu days. And j equals 3. There's 3 ranges. And here we have k equals 1, so it's just 1 sample per group. And that might seem a little weird with 1 sample per group, but because even though you only have 1 sample per group, because you have kind of 9 samples in the whole data set, you can still kind of do something. And that actually kind of brings me to kind of the next point, which is that there's going to be 2 cases we look at. The first case is k equals 1, and so that's like the example that we're seeing here. And the second case is k greater than 1, because we can see that we can actually we can actually kind of try to estimate a little bit more if k is bigger than 1. In particular, we can look at an interaction effect, which is not possible for k equals 1. And we'll kind of see sort of why that's the case. So I'm going to kind of first look at the first case. In some ways is easier. So case 1, k equals 1. So we have that we just have one sample within each of the samples. So we're just going to say our data here is just yij since k equals 1. Because, if you think about that range example, if k equals 1, like that subscript's always going to be 1, so there's no real value in including that. And then for our model, we have 2 factors. So we have that yij is like, we have the overall mean like we did for the one-way case. So if you're kind of like just want something to track back to, think about the one-way case. We have mu plus alpha I, which is kind of the effect of the menu. Then we have the effect of the range, and then we have noise. So here, remember that so mu is the overall mean effect. Alpha I is the effect of first factor. Okay, and then we also have this constraint like we did before. I equals 1 to I, alpha I is equal to 0. And then we have the beta j is the effect of the second factor. So in this case, that would be, so the first factor is the menu day, and the second factor is the range. Beta j is equal to 0 as well. And then epsilon ij is again that's the noise. And we once again kind of conveniently assume that the noise variances are the same. Okay, and so now let's again keep the 6 components in mind. So let's think about the estimators. Okay, so a lot of things stay pretty similar here. So mu hat is equal to okay, so the mu hat is the overall mean, and so we kind of estimate that as we did before. The alpha hat I is just as we did before. We have this this kind of the mean of the group, which is just yij, and then you need to subtract off the overall mean because it's the overall effects. This is the effect kind of minus the overall mean. It's the group effect. And then for beta hat j, we get something similar, but instead we're taking an average over the second component. Okay, and so I'm just going to leave it as an exercise. Compute mu hat. In this case, you're going to have alpha hat 1, alpha hat 2, alpha hat 3, beta hat 1, beta hat 2, beta hat 3 for the range example. Okay, and so this is kind of nothing particularly sort of different or new from what we've seen before, but here we have two effects, so we get a beta hat j as well. So now things start to be a little bit different if we look once we turn to the question of hypothesis testing. So for hypothesis testing, so I guess the fourth component when we're talking about hypothesis is the null hypothesis. And there's actually kind of two null hypotheses we could have here, and you could also have kind of both the null hypotheses together. And so we're just going to call it HA, which is just that alpha 1 equals alpha 2 equals alpha I is equal to 0. And that's just saying that there's no influence for first factor. And then there's also the null hypothesis that there's no influence for the second factor. And so this is the no influence for second factor. And you can certainly put these together quite easily and just say no influence for either factor, and the testing procedure kind of follows pretty naturally from there. And then the next thing is probably the most critical thing, and the thing that you kind of need to kind of get down pat most is the sum of squares decomposition, or I'll just say we call it the ANOVA decomposition. Plus the degrees of freedom. Yeah, and degrees of freedom start to become a really important concept in statistics, and so ANOVA is kind of the first time when you see sort of how it comes into play. So here we have I'm just gonna write it out first and then kind of define things. So SS total, and then you have the sum of squares, which is kind of due to the effect of A, the sum of squares due to the variability of B. And then we have this sum of squares error, and I'll define what all of those are shortly. So the SS tot, which is like kind of the overall kind of sum of squares of everything, is what is quite similar to what we had in the first one-way case. It's just Yij minus mu hat squared. Then the SSA, that like we had before, is the influence of alpha hat I squared, and then you have to multiply by j because you're summing over I and j. And then you have the effect of B, which is going to be I times. So again, this doesn't look too different. And then the SS error, which is equal to okay, so that essentially is like just the overall error when you subtract off the the estimates for your under your model. So alpha hat I, beta hat j, and mu hat squared. Okay, and so now let's think about the degrees of freedom here. So because you have ij samples in total, the degrees of freedom for the sum of squares total is just ij minus 1. For A, again, you're going to have I minus 1 degrees of freedom because you have the alpha i's, and so there's I of them, but then you also have this constraint that they have to add up to 0, which is why you lose 1. And similarly for SSB, you're going to have j minus 1 degrees of freedom. And then, you can kind of think about it in a couple of ways, but like the degrees of freedom kind of have to sum up. So this SS error, that's kind of the error under your model. The overall degrees of freedom here are just going to be I minus 1 times j minus 1. And that's what you kind of need to make sure that you should have the degrees of freedom adding up. So I minus 1 plus j minus 1 plus I minus 1 j minus 1 should add up to ij minus 1. Okay. And so that's going to kind of be the and I should also add that to estimate. So if we want to estimate sigma hat squared, we just use SS error divided by so sigma hat squared is equal to SS error divided by I minus 1 times j minus 1, because that's kind of if you look at that kind of makes the most sense if you consider the model that we're looking at here, and that corresponds exactly to the estimate that we used before for the within group sum of squares. So this is kind of an idea of this decomposition, and often the hardest degrees of freedom to work out is for the SS error, and you can actually, if you're confused, you can do that by just subtracting off like the total sum of total degrees of freedom minus the degrees of freedom of A and the degrees of freedom of B. And so this brings us to kind of the final thing, which is the ANOVA table and F. In this case, there's actually two tests because we're testing two hypotheses. So we'll say that we have in some sense we have factor 1, factor 2, then we have like error, and then we have total here. So the error here is kind of the influence of is if you kind of take away the variance explained by both factors 1 and 2, then you get an overall error. So if we look at the degrees of freedom, once again we have degrees of freedom, sum of squares, mean squared, and then the F. And so here we have, as I mentioned, we have I minus 1 degrees of freedom for the first factor, j minus 1 for the second factor, I minus 1 times j minus 1 for the two factors together, and then the total is ij minus 1. For the sum of squares, we've already kind of gone through that. It's SSA, SSB, and then SSE, and then we have the SS total. And so, as I mentioned in these columns, everything should, like the total should be the sum of everything in the three before. And then for the mean squared, we have these three mean squares that are important. And then we have the okay. And then for the F, we're going to get a different F for whether you're testing the, you remember there's two possible nulls. The A is not significant, and then the first factor is not significant, and the second factor is not significant. So in this case, you're actually going to look at SSA over I minus 1, and then you're going to, like we did for the one way, you're just going to kind of look at SSE divided by I minus 1, j minus 1. And similarly for the F for the B example, you're going to have SSB divided by j minus 1, and then we're going to divide that by the error. Okay, and so like in terms of the F test, if your null is HA, then under HA, you have that F, I'll call this FA, so that we'll call this FA, and we'll call this FB. FA is going to have the distribution of a F distribution with degrees of freedom I minus 1, and then I minus 1, j minus 1. And then under HB, under the null hypothesis HB, FB is going to be have the distribution of j minus 1, I minus 1 times j minus 1. Okay, and so that kind of gives you, the way to test these two different hypotheses. There's also ways you can kind of put that together and try to test both simultaneously. And I can talk to you more about that if you have questions about that. So you can so just to kind of leave this as an exercise. Find so I'll say, so fill in an over table and perform F test with alpha equals 0.05 for the energy slash range slash restaurant example that example that we saw earlier. And so that's a useful exercise to go through just to kind of make sure that you've got a grasp on the calculations. Now let's look at the second case here. K bigger than 1, so more than one sample per group or subgroup. Okay, and so the voting is a good example to think about because clearly you're going to have more than one person who has, who's from Wisconsin. In a poll, ideally, you'd have more than one person who's from Wisconsin who had a college level education and so on. So that's kind of a pretty common scenario. So in that case, you now have the subscript k. So your data here is yijk, where k is between 1 and k. So now you have that subscript. So, and obviously we have I between 1 and I, and j between 1 and j. Okay, and so now our model, we can actually, because we have more than one sample per group, we can actually have a bigger model. So you could certainly use what we did in the one-way case as our original model, but we can actually, if we want to be as general as possible, we can say that there's an effective factor A, there's an effective factor E, but then there's also an interaction effect potentially, and then there's noise. So we have here that mu is the overall effect or mean. Alpha I is the effective effect of the first factor. Beta j is the effect of the second factor. And then we have this new term delta ij, which is that this is the interaction effect of first and second factor. Okay, and so this is like, if you think about the example of state and education level, maybe there's some effect that, like being from, a college graduate from Wisconsin, has a different influence to being a college graduate from California, and there's some sort of interaction that you want to model. And so this is actually going to be sort of another hypothesis that we need to think about. And then we also have that epsilon ijk is just noise, and they're also independent. And once again, we're going to have these constraints. So we have the constraint that that there's no effect due to the overall effect of the groups of the ith factor is 0. The overall effects of the jth factor is 0. And then for the interactions, we actually have that summation I equals 1 I actually is equal to. So if you do a sum across either the state effects or the education effects, or the first factor or the second factor for any of the different groups or levels, they equal 0 because they've already kind of been taken care of with the alpha i's and the beta j's. So that's why we have these this additional set of constraints. Okay. And then if we're interested in the estimators, I mean, the only sort of really new and different thing that we're going to see here is the interaction. So when we had k equals 1, you actually can't measure this interaction because you don't have enough data to do it. Because, for example, if you have, in the menu, in the restaurant example where you're looking at energy, you only had 9 data points and there's going to be 9 interaction effects. So you don't really have enough data to do that. But now that you have k bigger than 1, you actually do have enough data to potentially estimate that interaction effect reliably. So a lot of things are quite intuitive here, but there's there's things we have to sort of worry about now because we have an additional interaction effect. So the overall mean is pretty intuitive, and we're doing a lot of triple sums here, which is going to be a bit annoying, but okay. Alpha hat I is again what you'd sort of basically expect. So remember that we want to subtract the overall mean. So this is just going to be and then we have that the beta hat j is we now have three subscripts. So I've got dot j dot here to indicate the mean here, and then we also want to subtract off the let me make this a little bit clearer. And so that is equal to okay. And so now comes kind of the new thing for the for this two-way case where k is bigger than 1. We have this delta hat ij, which, as you might expect, one of the terms is going to be yij dot. But then we have to think about, we need to subtract off the effect of group A, which is going to be y. And then we're going to subtract off the effect of group B. And then to kind of make everything add up, because alpha hat I kind of had, so the way to think about it is there's an overall mean associated with y bar ij dot in there. Then you subtract off an overall mean in the y bar I dot dot, and then you subtract off another in the j factor, and then you need to add that back. So that's why you have a y bar dot dot, and then we have that y bar ij dot is equal to 1 over k. So this is sorry. This is sorry. So this is going to be 1 over k. Okay, and so this gives us kind of the overall estimates that we need. Okay, and so this is again not reasonably intuitive, I think. As I said, the only thing that's really new is the interaction effect, and so the interaction effect is kind of the mean across the groups, but then you want to subtract off the mean due to the first factor, which is y bar I dot dot, and then you want to subtract off the mean due to the second factor, and then you also want to add back in the mean that you've lost. Okay, and so the next question is that you want to have the null hypothesis, and now we actually have 3 different null hypotheses. So I'm going to call the first one HA, which is just that alpha 1 equals alpha 2 equals alpha I is equal to 0. Then we're going to have the second null, which again is exactly the same as what we saw in the previous case with k equal to 0, that there's no. So this is just saying the first factor has no influence. This is saying the second factor has no influence. And then we also now have a third set of parameters, which is the HAB. And so I'm going to call this HAB, which is just because we're calling the effects A and B. So we're just going to say delta equals, and then it's basically just saying that all of the deltas are equal to 0. So this is delta. So all of the deltas are equal to 0. And this is just saying that there's no interaction effect. So because we have now 3 different null hypotheses, we're going to get 3 different F statistics out of this. Okay, and so we're going to have basically one extra term. So this is where we're going to have the ANOVA decomposition plus, I'll say, yeah, plus degrees of freedom. Okay. And so here we're just, it's going to be very similar, but we are again going to have one extra term. So we have SSA plus SSB plus SSAB plus SSE. And the SSAB comes from the fact that we have this interaction effect. So let's see, how do we define things? So once again, SS tot is going to be like what we had before here. It's going to be yijk minus the overall mean squared. The SSA is going to be summation I equals 1 to I of alpha hat I squared. And we're going to need to multiply this by a factor of j times k to ensure that, because we have the extra sums of j and k that we're not, that need to be included here. SSB is equal to I times k of the, now we sum over the beta hat j squareds. And then we have now our SSAB, which is our interaction term, which is going to be k times summation I equals 1 to I, j equals 1 to j of delta hat ij squareds. And then we're going to have our SS error, which is, we're like we did before. So the principle is very similar. We have our overall yijk, and then we're going to subtract off a mean, and then but then also the model that we have here. So minus alpha hat I minus beta hat j minus delta hat ij squared. Okay, now let's look at the degrees of freedom that we have here. So as you can kind of intuitively expect, for the SS total, we have ijk sample, so it's going to be ijk minus 1. For A and B, it's very similar. We're again going to get I minus 1 and j minus 1. For SSAB, we're going to get I minus 1 times j minus 1. Because, we have each of these constraints. So I minus 1 comes from the fact that we have the sum, like the I different alphas plus you have the constraint, and then you have the j different betas plus the constraint. The I minus 1, j minus 1 comes from the fact that, we have the ij different deltas, but then you have the constraints. And so that's why you kind of need to subtract off the I minus 1 times j minus 1. And then for the overall sum of squares, this is like actually in some ways more intuitive to think about. You have ij different groups, and for each of those you have k minus 1, k minus 1, because you lose 1 degree of freedom for estimating the mean of each of those groups. So you have ij times k minus 1 as the degrees of freedom, and you should check that this whole thing adds up. So ij times k minus 1 plus I minus 1 times j minus 1 plus j minus 1 plus I minus 1 should give you the overall degrees of freedom of ijk minus 1. Okay, so this is kind of the key point, and then I should also mention that to estimate, again, you don't need this for the f-test, but if you wanted to estimate sigma hat squared, you can again just use the sum of squares error and then divide by the degrees of freedom for this thing. Okay, so now we're kind of close now to being able to put things together for the ANOVA table and the f-test, which is kind of a summary of everything. So for if we want the ANOVA table plus the f-test, we have again, we have factor 1, factor 2, then we have the interaction, and then we have the error. And then we have the total. So now we have 5 rows that we need to think about here, because we have 5 terms in the expression. So if we look at degrees of freedom, sum of squares, and then we have mean squares, and then the f. Okay. So for factor 1, we know that there's I minus 1. So for the first 2 columns, I'm really just summarizing what we already did. And then we have, we have ijk minus 1. And then for the sum of squares, again, we've already calculated this, but we want to put it on the table here. Okay, and as I mentioned again, everything should add up in the first 2 columns. So the sum of squares total should be the sum of those other 4 sum of squares, and then the degrees of freedom should also add up. And then we're going to get we're interested in this is just the sum of squares divided by the degrees of freedom. Okay, and then once again, we're going to get 3 Fs because we have 3 different null hypotheses. So I'm going to call this like Fa is going to be, and then we want to kind of derive by the SSE. Then we have FB, which is equal to and then we have FAB, which is equal to SSAB. And then once again, we compare that to SSE, which is ij times k minus 1. Okay, and so now we're pretty close to done. And now if we want to do our f-tests, we have that under HA, so the null hypothesis A, we have that FA should have a F distribution with I minus 1 and then ij times k minus 1 degrees of freedom. Then under the second null hypothesis, we have that FB is Fj minus 1 ij times k minus 1. And then under the third null hypothesis, which is HAB, we have that FAB should have an F distribution which has I minus 1, j minus 1, and then ij k minus 1. So this kind of gives you like a simple way to do these different tests. And so so just kind of in so the ANOVA summary, because I guess like the way to think about using this, I mean, what you need to know for the final is just how to basically do these cases. So there's 3 different cases of ANOVA that we've seen, and you've seen how to do that. But ANOVA is a really powerful tool, because then the question becomes, what if you have 3 factors or 4 factors and so on? And so in some sense, like this really lays the foundation for a very general framework that allows you to test various different hypotheses and do various do estimation under various different models. So there's really kind of like 6 components. There's 6 components to this, because there's both estimation and testing involved in this. The first one is the data, and that's really sort of like which groups do we so like we have groups plus samples per group is really the key thing there. So we're going to have like either double or triple subscripts. The second component is the model. And then there's, and so remember that there's there's 3 cases. There's like 1 is one way, 2 is two-way, and that's with k equals to 1. And then the third one is two-way. Sorry, let me write this. It's two-way with k greater than 1. And so let me maybe be a little bit more explicit here. Here, so for the first case, obviously we have Yij as our data. For the second case, we also have Yij, but as we see, the model will be different. And for the third case, we have Yijk, because now we have more than k samples per group. And then for our model, I'm summarizing this, so there are a few things that I'm not going to include, because this is just kind of a bit of a summary. So for one way, we have just mu plus alpha I plus epsilon ij. And then you obviously have the constraints, which I'm not going to put in here. For the second case, we have mu plus alpha I plus beta j plus epsilon ij. So this is like, you have like the factor 1 and factor 2 here, but no interaction term. And then the third case is Yijk is okay. And then you have the rest I'm kind of not going to spend too much time on, because and I forgot to mention, there are obviously these constraints in the distribution of normality, which I'm not going to put in because I've gone through those in detail earlier, but you can kind of see how how these different setups compare. The third component is the estimators. The estimators, and they are all basically kind of related to the overall means or means of groups. The fourth component is the hypotheses, and or I should say the null hypotheses. And again, for the first case, there's only one null that we're interested in. For the second case, there's 2 nulls that we're interested in. And for the the second null is HB, which is Okay, and then for the third case, we have like, so maybe I'll just write it this way. This is probably easier. Essentially, there's three different nulls, and they correspond to like setting like a set of parameters in the model to 0. Okay, and so this corresponds to the first one. So I guess this like the first one, or like the A hypothesis corresponds to, I'll say, 1, 2, and 3. The second one corresponds to 2 and 3. And the third one just corresponds to 3. We're testing the interaction effects. And then probably the most critical part to kind of understand and to get your head around is the ANOVA decomposition plus degrees of freedom. I think, yeah, the degrees of freedom are often quite, it takes a bit of time to kind of get your head around it. I think maybe the best way to think about it is like the amount of data that you have, kind of minus the number of parameters that you lose, and that's sort of maybe the best way to interpret that. But yeah, like I think just trying to kind of get your head around where the degrees of freedom are in these different cases is worth spending some time on. And then once you've done 5 well, the sixth part is really hopefully just filling in a table. So that's just the ANOVA table plus the F tests. So I think really sort of the majority of the work, or the challenge really lies in that fifth component of understanding the degrees of freedom. Okay, and so that's kind of everything that we'll be covering in chapter 12 on ANOVA, and that should sort of allow you to answer all the questions that are posed in homework 10. Okay, so thanks very much, and have a good rest of your day. Thanks.